Hi friends, welcome to follow up. Let's have a look at problem 456, 132 pattern. In this video, we're going to explain a solution based on monotonic stack. First, let's look at the problem statement. So here we are given an integer array called nums. So we want to find if 132 pattern exists or not. So here, 132 pattern is a subsequence of three integers corresponding to nums I, nums j, nums k. The index order is I less than j less than k, and the number order is nums I less than nums k, the third index, and then less than the second index number, that is nums j. So this problem, if we do not do coding and we use our intuition to check, it's actually very simple. So for example, in example 1, so this list is strictly increasing, so we do not have 132 pattern, so the output is false. And in example 2, so because we want to find a smaller one, then we jump to a larger one, then jump to a slightly smaller one, so we have 1 for 2, so this is a valid one, so we return true. In example 3, so also the output is true, so actually such patterns are not unique. For example, you can look at -1, 3, then you can either end with 2 or 0, because both 2 and 0 are less than 3 and greater than -1. Or you can see -1 and the middle one is 2 and the last one is 0, right? So here I want to point out that so the length of this list can be as long as 2 times 10 to the power 5. In other words, we need to consider time complexity if we do the coding part. So with that said, let's look at the analysis. So here for this problem, so if we use a very brute force solution, so we can use a 3-layer for loop, right? We iterate for all the indices and then we compare this relation. If such a relation holds, so we are going to return true, otherwise we are going to return false. However, if we assume that the length of this list, nums or capital A, so is n, this 3-layer loop solution will be O n of 3, as roughly can be reached as to 10 to the power 15. For sure, this will not pass the test. So for this problem, actually it provides a good example for using monotonic stack. So here we want to take a strategy that I'll first explain the coding and the code part, and in between we are going to explain the logic and what matters a lot is that we digest or understand 2 subtle points. So with that said, let's continue. So here I'm going to track the length of this nums list. So here I change to capital A just for convenience of writing, and then I'm going to track an edge case. So this is very important. So if n is less than 3, so we can directly return false, right? And the reason is that we need to have at least 3 numbers to have such a pattern. So with this case excluded, now let's look at the general case. So we are going to use 2 ingredients. So 2 ingredients. So the first one is a mean list. So basically, we want to find for an index the minimum number up to that index. So another one is monotonic stack, the main trick. So here, let's first get the mean left list. So I'm going to initialize it like this. So here, let's define mean left. Say for index I, it will be the mean of nums or A up to index I and inclusive. Let's write I plus 1 here, right? So for this, mean left 0 is very easy to determine. That is A of 0 or A naught. And then let's set other ones. So for I in range 1 to n, right? So by the definition of mean left I, so mean left I will be the minimum up to index I minus 1. Look at the indexing here. We are starting from 1, so I minus 1 is valid one. So or it's at least 0. So in index, right? So then the current number will be a of I. So this way we are going to get this mean left list. So here is a quick remark before we move forward. So mean left is non-increasing, right? Because we are taking minimum, and the more number we have, we are going to get maybe even smaller minimum, right? So this is very simple to reason. So next, let's initialize the monotonic stack. So when we use this one, we first need to make it clear what we want to store in the stack. First, we want to store the numbers, and we want to store the third number in a potential pattern. So 132 pattern. Let's see. So this is what we want to first make clear. So next we are going to do the iteration, but here the order of iteration is very important. So for j in range, so we are going to iterate reversely. So this is the end, not inclusive, -1. This is the increment, this is -1, that is decrement by 1. So in other words, we start from the last index and ending at the index 0. And then what we want to do, so we want to check if the current one is greater than the mean left j, right? So if the current one is strictly larger than the one corresponding to the minimum, so it's a potential for the third number, right? In this case, so we are going to do something, or you can think of other. Else, if this aj is less than or equal to the mean up to this one, because it's too small, it cannot serve as a third number in a potential pattern. So we are going to continue. So so let's write like this. We just focus on the case when aj is strictly larger than mean left. So what we want to do actually is this. So we want to stack append this aj. The reason is that, so if this aj can potentially serve as a third number in 132 pattern, but also, if the stack has already something and we are in the middle of an index, we need to check if we already have 132 pattern. So here is like this. We could check if the current aj can serve as the second number in the pattern, right? So notice that you can think of, when I look at this index, so there might be some element already in the stack, that those elements correspond to the third number. So now let's do the check. So here the check is the very condition, the very monotonic stack condition. So this is actually a pattern. If you used or practiced quite a lot on this kind of problem, so you will recognize this very quickly. So first we are going to do while stack, and stack -1 is less than or equal to mean left j. So if this is the case, for sure this stack -1 cannot serve as the second element, right? So what we want to do is, let's see. What we want to do is we do stack pop. Then this is a very typical monotonic stack pattern. So after we exit this while loop, there are two cases. Either stack is empty, right? In that case, we didn't find any pattern, or the stack is not empty, and then stack the top element will be strictly larger than mean left up to this index. So in this case, we can do a check. If stack is not empty and stack -1, so because if the stack is not empty, we can guarantee stack -1 will be larger than mean left j. In other words, to the left of the index, or to the left of this number, there is at least one number is strictly less than this stack negative 1. If stack negative 1 so is less than a of g, right? This means the third one, because the stack will store the third element. The third element will be less than the second element. But we know stack negative 1 already larger than this min left. So we are going to return true. This is the condition. So here, then we add this one. So finally, after this one, we actually return a false. So this forms a full solution to this problem. So before we make any comments, let's first do a test. So it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. So here I want to ask several questions. First, for this one, when we do add, so at the very beginning, for AG, so this case I want to make, so we want to add AG to a potential third point. So therefore, you want to, as such, we know that the stack elements are potential third points when we are examining the current or an index G, right? So this index, you should understand it as a generic one. So if we look at this pattern of this code, right, if we do not consider this part, so let's first comment out this part, right? So what we are doing is that if AG is strictly larger than the min left, then we are going to append this AG to the stack. Basically said that we find a potential third number, right? So this is the part. So now if we include this part, so this monotonic check basically says that as in my stack, we already have a potential third point. So I want to check if the current AG can be serving as the second point. So then we do monotonic stack to make it the top element in the stack will be strictly larger than the min left, right? So then if the top element is less than the current AG, it basically means that AG can serve as the second point in the pattern. Then in this case, we are going to return true. So this is the first comment. Another comment is that why we iterate for G from right to left. So this actually is connected with the min left. As we remarked, min left is non-increasing, right? If we look at the pattern, so for the G, right, if AG is greater than min left G, you can think of G is very large, then we're going to add that, and also we are going to do this min monotonic stack. So the output of this while loop state will be that the top element in the stack, if any, will be strictly larger than the min left, right? And then if we look at a smaller index, in other words, to the left, and then in view of the min left is, if we look at from right to left, it's actually increasing, right? If we look at the min left from left to right, it's non-increasing. So in this case, we know that the smaller the G, the min left is the larger. So we don't need to move back, so we can continue at where last step stops. So that's the two key points. So here let me summarize the 2 points. So the first one is that so the stack stores elements for potential third point in the pattern, in a potential pattern. And when we use monotonic stack, we need also check if we can use a current number, let's say AJ, serving as a second point, right? This is the one. Another point is that mean left is non-decreasing, looking from right to left. So that's also the reason for iterating from right to left when we do monotonic stack. This is due to the monotonicity of this this list, right? So this is very important. Actually, if you see this code as a whole, it's designed very elegantly, right? So with that said, basically that's about it for this specific problem. So I would suggest that you take some time to digest the logic and digest the design pattern for writing this code. So with that said, I guess that's about it for this video. Thank you.